A dynamic routing protocol helps a router build the big picture of the network. It adapts to changes and makes configuration simpler. We're going to start the routing protocol journey by looking at RIP, one of the simplest and oldest routing protocols in use today. RIP, or Routing Information Protocol, has been around for quite some time. Okay, maybe not quite as old as the routers shown here, but still, it's a grandpa of routing protocols. RIP comes from the days when all addressing was classful. As we started moving away from classful addressing, RIP needed to be updated to version 2, which is now classless. The whole point of RIP and other dynamic routing protocols is to share routes with neighboring routers. This way, each router learns about routes to other parts of the network and can decide on the best way to get there. This can be used instead of or along with static routing. RIP, being a very simple routing protocol, is a very good place to start learning. The concepts learned here can be extended to other routing protocols like OSPF or EIGRP. And if you're looking to practice, we have some very good labs at the end of the video. But before we dive right into RIP configuration, let's talk about dynamic routing protocols in general. We can break routing protocols into two categories, distance vector and link state. These are two entirely different approaches to how a routing protocol works. At a high level, we can say that a router running a link state routing protocol builds a full map of the network. Each router shares information on each path they know about with their neighbors. These neighbors pass this information on to their neighbors, and so on. The result is that every router builds the same map of the network. Distance vector routing protocols, which includes RIP, takes a different approach. Routers running a distance vector protocol will still share routing information with their neighbors, but they won't share as much information and they won't build a full map. Simply put, they share a network and how far away it is. For example, a router might say, I know about 10, 10, 10, 0, and it is 2 hops away. In this example, the distance is how far away the network is, and the vector is the direction the network is in. The network direction, you might say. And that's how we get the name distance vector. This makes distance vector routing protocols less like a map and more like signposts pointing the way. If a router gets an update for the same network from two different neighbors, it will look at the distance and use the path that it thinks is better. We'll see this in detail soon. But for now, we should start getting our hands dirty with RIP configuration, using the same topology that we've used for the last few videos. At this point, there's no static routing configured. To start with, we simply enter router RIP to start the RIP process. On a Cisco router, all routing protocols run as separate processes, which only runs if we use this router command. This is also where most of our RIP configuration goes. For example, we can now enter the command version 2. Remember that we can use RIP version 1 and RIP version 2. RIP v1 should never be used anymore, so this command forces us to use RIP v2 only. Our next step is to use the network statement. This is sometimes misunderstood, so I suggest paying attention to this one. The network statement enables RIP to send messages on any interface with an IP that's covered by this range. You might notice there's no subnet mask used with this command. Even though RIP v2 supports classless networks, this command is still classful. So when we entered network 172.16.0.0 on R1, we told RIP that it is allowed to send update messages on the 4 gigabit interfaces, as they all have IP addresses in the 172.16.0.0/16 network. These messages are sent regularly and contain a list of networks that this router knows about. RIP v1 broadcasts these messages to all hosts on the network. RIP v2 is a little more elegant and sends them to multicast address 224.0.0.9. Sending these update messages to a multicast address means that only routers listening for RIP messages will get them. This is much more efficient than a broadcast. RIP messages will not be sent further than a single hop. So, for example, if R1 starts sending updates to R2, R2 will not forward these messages to R3. It may create and send its own update messages, but it won't forward the exact message it received from R1. We also need to use a network statement for 10.0.0.0. But there aren't any routers connected to the 10.0.0.0 networks, so why would we want to do that? In addition to enabling interfaces to send updates, the network statement will also tell the router that it's allowed to advertise the connected networks in that range. And here's the bit that sometimes confuses people. I know it confused me at first. The purpose of this command is not to advertise 10.0.0.0. The purpose is to advertise any connected network within 10.0.0.0. Of course, for this to be useful, we need to enable RIP on another router. Over on R2, we're putting in the exact same configuration. Part of enabling RIP is not just sending out update messages, but also being able to receive and process them. We can see this in action with the show IP protocols command. This command gives us information on all routing protocols configured on the router. It just so happens that RIP is the only one we have configured right now. In the RIP section, we can see the routes that we've added with the network command. We can also see routing information sources, which is a list of the routers that are sending RIP updates to us. When a router sends these updates to other routers, it will use the IP of the egress interface as the source IP. If you're not familiar with the term egress, it refers to traffic leaving the router. So if a router sends a RIP update out the GI01 interface, it will use the GI01 IP as the source address. This probably sounds obvious, so why am I talking about it? Because of the way the receiving router handles this message. The update message contains a list of several networks, and all these networks go into the RIP database. Ultimately, some of these may end up in the routing table. When this happens, the router will use the IP address listed as the source IP in the update message as the next hop. Now that the router has learned about some networks, it can share them with its neighbors using its interface as the source IP. In this way, all routers through the network can learn the routes. If we go back to our lab topology and look in the routing table, we can see that we have now learned some RIP routes on R2 and that R1's IP is the next hop. You'll also notice a timer next to the route. This is how long it's been since the router has heard an update on this route. And of course, we can filter the routing table for RIP routes only if we want to, just like we did with static routes a few videos ago. It's now time to share something really interesting. RIP v2 isn't classful like RIP v1 was. However, it still has some classful roots. We saw an example of this with the network statement earlier, no subnet mask. Another thing that RIP v2 will do by default is to summarize to a classful network. Look at R1. It has 3/24 networks in the 10.1 range. RIP will not advertise each of these networks. Instead, it will automatically summarize these into the classful 10.0.0.0/8 network, and it will advertise that instead. It's essentially saying, if you want to reach anything in the 10 range, send traffic to me. But can you see where this might be a problem? Look at R4. It also has networks in the 10.0.0.0 range. So it will also advertise the exact same summary route. Poor old R5 is going to get the same route, 10.0.0.0/8, advertised from both R1 and R4. It then has to choose between the two of these so one can go in the routing table. LPM and administrative distance are the same in both cases, so they won't help. The end result is that R5 won't have all the information it needs to make a good decision. The solution then is to disable auto summary on each RIP router. This tells RIP not to do any summarization unless we tell it to, causing it to send the real /24 routes. I recommend always disabling auto summarization. Summarization itself is not a bad thing. In fact, although it's a bit too advanced to get into right now, summarization is really useful. But we want to control this ourselves. We don't want the router automatically doing this for us. We should now do the same on R1, of course. And if we look at the routing table, we can see the correct routes. This is a good time to pause and to review what we've covered so far. While you were looking at the quiz, I've quickly added all the RIP config that we've just seen to the rest of the network so we can focus on the next big thing. Remember the network statement we used earlier? It enables RIP messages on our router's interfaces, and it advertises connected routes. What would you do though if you were faced with a situation where you had to advertise a connected network, but you don't want to enable RIP messages on a particular interface? For example, take a look at R5. It's connected to an ISP router, which is managed by a third party. We generally wouldn't want RIP sending our routing information to a third party, but we still want to advertise the 172.16.200.0 to the rest of our network. To solve this problem, we can configure an interface as a passive interface. We'll do this for GI0/1, which connects R1 to R5. RIP messages are no longer sent out of GI01, but its connected network is still advertised. Show IP protocols shows us that this interface is indeed excluded from RIP. Let's put that back in for now and look at an alternative approach. I prefer this method myself, which is to set all interfaces as passive by default. We then disable this on any interface that we do want to participate in RIP. I find this to be a bit more secure, as we can't accidentally have RIP turned on. Notice here that the loopback interfaces are now missing from this list. Seeing as we've mentioned security, another option available to us is authentication. We can require each of our routers to include an authentication string in their update messages. Routers that receive these messages will check if the string is correct before accepting these updates. This is done to protect against rogue routers. Imagine a silly scenario where someone in your office bought in a router from home and connected it to the network. They could use this to influence how routing works, which is completely unacceptable to us. If we configure authentication, we can prevent this from happening. So let's configure the link between R1 and R2 to use authentication. We start by defining a keychain. This is a list of passwords that we can use. On a Cisco router, keychains can be used for all sorts of things, not just RIP. Inside the keychain, we create a key. The key is our password. If we wanted, we could create several keys and have our routers cycle through them periodically, but that's a bit advanced for now, so we'll just stick to one. Unlike most other RIP configuration, we apply this directly to an interface. This is because we could use different keychains for each interface if we wanted to, or perhaps enable it on some interfaces but not on others. First, we need to set the type of encryption. This can be set to plaintext or MD5. We don't want to use plaintext, as this would send the password without encrypting it first, meaning a hacker or someone malicious could read the password with very little effort. MD5, on the other hand, encrypts the password before it sends it. And second, we choose the keychain that we want to use. Of course, we then need to go to R2 and configure the settings there as well. If we don't have the config matching between the two routers, they won't be able to share routes. If we show IP protocols now, we can see the keychain listed. This is handy for troubleshooting. Let's take some time to consider something that's critical to routing protocols: the metric. A metric is simply a way to measure something. Metrics for time include seconds, minutes, hours. Metrics for weight includes kilograms and pounds. A distance vector routing protocol uses a metric to measure the distance from the local router to the destination network. RIP uses hop count as its metric. For example, from R1, the network 10610 is 2 hops away using this path. It is also 3 hops away using this path, and 3 hops away using this third path. R1 will learn about the 1061 network from R5, R3, and R2. It won't build a map of every link beyond these routers. It just uses these as signposts. This is how distance vector routing protocols are different from link state. What it will do is it will look at the hop count, and it will find that one path is shorter than the rest. In RIP's mind, the shortest path is always the best path. So it takes this information and it puts it in the RIP database. We can take a look inside the database with show IP RIP database if we want to. See our path to 10610 with the number 2 next to it? 2 is the hop count. You might notice that some networks have more than one entry in here. This happens if there is more than one path with the exact same metric. Routes from the RIP database are offered to the routing table. If these have the best administrative distance, the router will put these routes into the routing table. Looking at the routing table now, we can see the route to 10610, and next to it is the administrative distance, 120, and the metric, 2 hops. All routing protocols make use of a metric of some sort. OSPF, for example, gives each link a cost, which is based on how fast the link is. Slower links have a higher cost, which are less preferable. EIGRP uses several bits of information to make a metric, including bandwidth, latency, load, and reliability. Often EIGRP metrics are very large numbers. The important thing to remember is that each routing protocol will select the best paths it knows. It will offer these to the router to use in the routing table, and the router will select the best route using administrative distance. Are you comfortable with this so far? Here's a couple of questions to see if you're really getting it. We should really take some time to talk about 2 key characteristics of distance vector routing protocols. These are split horizon and route poisoning. When we configure routes, we need to be careful not to create loops in the network. If you've been trying out labs in the last few videos, you will have seen where this can go wrong. Dynamic routing protocols are no exception. They also need to prevent loops occurring in the network. One of the ways they do this is with the split horizon rule. Imagine that a router receives information about a route from a neighboring router. This will say, use R1 to get to this network. One of the things this router will need to do is share this update with its other neighbors. How does it do this? The simple way is to send a message out each interface saying, use R2 to get to this network. Unfortunately, this comes with a problem. R1 is telling R2 how to get to the network. At the same time, R2 is now telling R1 how to get to the network. A packet flowing through here may be forwarded to R1, which then gets forwarded back to R2, and then gets stuck in an infinite loop. So to solve this, the split horizon rule simply says, when a routing update is received, send it out all interfaces except the one it was received on. So in this case, R2 will send an update to R3 and R4, but it will not send it back to R1. Simple and elegant, isn't it? Another elegant solution is how bad routes are handled. Imagine that R1 is connected to a network that goes down for some reason. R1 will now want to advertise that this network is gone, so other routers can remove this path from their routing tables. To do this, it sends a network update that marks this route as unreachable. The way this is done depends on the routing protocol. RIP has a hop count as a metric. The maximum hop count RIP will allow is 15. So if R1 wants to tell the entire network that a particular network has been lost, it can set the metric to 16. This is an invalid hop count, so other routers that receive this update will see this path as invalid for this network. To put it another way, this route is marked as unusable. This will be left in the routing table for a short time, and then it will be removed. And this brings us to a concept called convergence. Let's consider what would happen if R3 failed, perhaps due to an unexpected power outage. R1 and R3 are directly connected together. When R3 fails, the link between R3 and R1 goes down, causing R1's interface to go down as well. R1 can immediately see that there's a problem and can start working on finding alternate paths through the network. Recalculating paths when there are changes in the network is called convergence. What about the routers that are not directly connected? Take a look at the path between R3 and R5. They may be one hop away, but they're not directly connected. There is a switch in between. So, if R3 were to fail, the link from R3 to the switch will go down too. However, the link from R5 to the switch will not go down. R5 will not immediately know that R3 is down, so it needs some other way to discover this and to converge. To handle this, RIP uses 4 different timers. The first is the update timer. This is how frequently route update messages are sent. The next is the invalid timer. This timer tracks how long it's been since a route has been updated. Each individual route has its own timer. Every time a route update message comes in, this timer resets to 0, so in a healthy network, this timer will be reset every 30 seconds. If this timer counts up to 180 seconds without receiving an update, then something is clearly wrong, and this would be the case if R3 failed. The router will mark this route as invalid. This is also called the hold down state. When a route enters the hold down state, the hold down timer starts. During this time, no updates for this route will be accepted. This stabilizes the routing table while it's converging. That is, it gives the router enough time to find another valid path before flooding it with new information. And the final timer is the flush timer. This begins at the same time as the invalid timer, but it counts up a lot higher. It also resets when new updates come in as well. By default, this is 60 seconds longer than the invalid timer. This means that for this 60-second overlap, the router will advertise that the route is invalid to its neighbors. This is when it's using the metric of 16. When this timer finally expires, an invalid route will be removed from the routing table. These timers, at least in their default values, are very high. Because of this, it can take several minutes for a network to fully converge when there's a problem. This is one way that RIP is significantly inferior to other routing protocols. So how do we manage the default route? We can't simply throw in a network statement for 0000 and expect it to work. Why is this? Because it doesn't match any connected route. We can't advertise a route that we don't own. We could configure a static route on all routers, but that's a lot of effort, and it won't respond to changes in the network. What we can do is pick the router closest to the internet and configure a static default route there. Then we can use RIP to advertise this default route to the rest of the network. This is simply done with the default information originate command. We could use this command without the static route, but that would cause a problem. Once the traffic reaches R5, R5 will need to know what to do with it. So it still needs a default route in its routing table. And to verify this, we can log on to R2 and see that it's learning the default route through RIP. In fact, it happens to be learning 2 usable paths. Are you ready to try this for yourself? I have 2 challenges for you. The first is simple. Take the topology and configure RIP everywhere. Remember to add in a default route, and if you're feeling adventurous, try configuring authentication. Next, if you're a member or you want to become one, you can download the second challenge from our website. This has RIP configured, but it's broken, and you need to troubleshoot it. I recommend trying this if you can. You will learn a lot from this practice. So, what do you think of RIP? Here's my personal opinion. I don't like using RIP in the real world. I think it's fantastic to learn from, but the other routing protocols are so much better. Its hop count metric is a pain as it doesn't take link speed into account, it uses classful network statements, and it takes far too long to converge. It really is a good starting point before learning other routing protocols though, as it's so simple, so don't forsake RIP as a learning tool. It will help you to learn the others later on. Thank you for joining me on this introduction to routing journey. I hope you've enjoyed it.